Good morning, Chem 20s. Our lesson today is going to be a continuation of yesterday's lesson. Today we're going to look at percent yield. Percent yield is the ratio of the difference between the actual or the experimental quantity of a product obtained compared to the predicted or theoretical quantity of product obtained using stoichiometry calculations. We use stoichiometry to do one of four things: to evaluate the overall experiment. It can test for experimental designs, technological skills, purity of the chemicals, and the quantitative nature of the actual reaction. Now, the formula for percent yield is actually pretty straightforward. You put the actual yield on top, you divide it by the theoretical yield, and then you multiply by 100%. The key to this formula is it does not matter what the unit is for actual or theoretical yield as long as they are both the same. So in some examples, it might be masses, so grams, grams. In some examples, it might be liters, liters, or it is possible that it could even be moles, moles. If the actual and theoretical yields are the exact same, the percent yield is said to be 100%. However, usually percent yield is lower than 100% because the actual yield is often less than the theoretical. This can be due to many, many reasons. Some of those reasons might be limitations in the measuring equipment, purity of the grade of chemical we are using, loss of sample during recovery. So if I'm going to, let's say, use filter paper, some of the particles might be so small, those fine little particles, that they might slip through, so we're getting a less accurate value. We could be using qualitative judgments that affect measurements. So when we do, let's say, a titration and we have to see a change in color, that is a personal judgment. What tint of orange or what tint of yellow or pink we're actually seeing to know when we stop the reaction. Or it is possible that we have an incomplete or possibly competing reactions when I mix some chemicals together. Well, let's try one example. So, example number one, given the reaction below, if 24.8 grams of calcium carbonate is heated and produces 13.1 grams of calcium oxide, what is the theoretical yield of calcium oxide? Use stoichiometry to calculate the theoretical yield of CaO. So first thing we're going to do is we have a balanced chemical reaction. If I take a look at it, it's already balanced. So that's the one thing when they give me a reaction, I do want to check that it's always balanced. Now what we're going to do is let's put our knowns and unknowns underneath. So if I take a look, we have 24.8 grams of calcium oxide. So that's going to go over here. 24.8 grams. The moment I have a mass, I can calculate molar mass. So I am going to add 40.08 plus 12.01 plus 3 times 16, and my molar mass is going to be 100.09 grams per mole. Now in the question, it tells me we have a mass of CaO. However, that is the actual mass. I would like to find the theoretical mass. Now, one of the most important things that most students ask is, Mr. Kemp, when they give me both masses, how do I know that I am trying to find the product mass, not the reactant mass? And I want us to think about what we're solving for. We are finding percent yield, meaning we are trying to find what is coming out of the product, right? If we have a cornfield, the purpose of a cornfield is to yield corn. So when I find percent yield, my job is to find what comes out of this chemical reaction. In this case, calcium oxide. So I am always solving for some sort of value of the product. Again, I can find the molar mass of CaO. So it's going to be 40.08 plus 16. This one's going to be 56.08 grams per mole. So Following the rules of yesterday, step number 1, where do I have enough information to solve for moles? So I can find the moles of CaCO3. I am going to take mass over molar mass. 24.8 grams over 100.09 grams per mole. So 24.8 divided by 100.09. My answer is going to be, if I look back 3 sig figs, 0.248 moles. My next step is, now that I know the moles of calcium carbonate, can I find the moles of calcium oxide? And we do that by doing a mole ratio. So take the moles we already know, and we're going to play a little game of leapfrog. So since I know these moles is 0.248 moles, I'm going to multiply by 1 mole of calcium oxide and divide by 1 mole of calcium carbonate. Remember, it's unknown over known. So it's going to be 1 mole over 1 mole. So my number is not going to change. And again, you're using the full number out of your calculator. Last but not least, now that I know the moles of calcium oxide and the molar mass, I can find mass. If you need to go off to the side to move the formula around, to move it around correctly, please do that. We're going to sub in our number, but again, we're going to use the full calculator number off of our calculator, and we're going to multiply it by 56.08 grams per mole. And my answer is 13.9 grams. Now, just to give us a little bit more room, we have now calculated the theoretical value of calcium oxide. What we would like to do now is find percent yield. And to find percent yield, our new formula is actual yield over theoretical yield times 100%. And I am just fine if you write actual over theoretical. So my actual value, if I go back to the question, is 13.1 grams. The theoretical yield I calculated by doing stoichiometry was 13.9. And remember, use your full calculator number. And then we have to multiply our value by 100%. So to find percent yield, 13.1 divided by second function answer, and times by 100%. And in 3 sig figs, my answer is 94.3%. Now, what we tend to like to do, if we were in Chem 30, is come back to the question and put this value on top of the arrow, which means if calcium carbonate, when it decomposes, about 94.3% of it wants to go to products. It doesn't all entirely go to products, and we're going to have a bigger discussion on this when we get to Chemistry 30 on some of the possible reasons why. Now, if we take a look at this, let's try to see if we can figure out marks. Since they already gave us the balanced chemical reaction, you don't get a mark for that. You get a mark for calculating moles. You get a mark for doing the mole ratio and calculating moles of the substance we're trying to find. You get a mark for answering the problem. You get a mark for the process, so formula and substitution for percent yield. You get a mark for your answer for percent yield. And then you get an additional mark, a 6th mark, for having 3 sig figs down the page, units everywhere, and of course, ideally, it would be states in the equation, but we already had that given to us, so this question would be out of 6. Excuse me. Question number 2. Why don't you copy the question, pause the video, and get as far as you can on this, and then unpause the video to check your work. When silicon dioxide is heated with an excess of carbon, silicon carbide is produced according to the following equation. The percent yield of silicon carbide is 96.7%. So I'm actually going to write this above here. If you started with 50 grams of silicon dioxide, so that's going to be my mass, which means right away I can calculate molar mass. Now, silicon is 28.09 plus 16 plus 16. Molar mass is 60.09 grams per mole. How much silicon carbide? So this is what we're trying to find. Okay, which means I again can look up the molar mass. And silicon is 28.09 plus 12.01, 40.10 grams per mole. So again, I have enough information for silicon dioxide that I can find the moles, mass over molar mass. So I'm going to take 50.0 grams divided by 60.09 grams per mole. I go back to the question. I have 3 sig figs. So my answer is going to be 0.832 moles. Again, if I know the moles for silicon dioxide, I can find the moles of silicon carbide using a mole ratio. And it's unknown 1 over known 1. So 1 mole over 1 mole. I know it seems like it's silly to do this step when it's 1-to-1, but that's the only way you can show your teacher or anybody else who's looking at your problem that you understand why the moles of silicon dioxide are the same as the moles of silicon carbide. You're doing a process, you're doing a mole ratio to show that the 1-to-1 ratio does not change that number. Last but not least, we can find the mass of silicon carbide. So that's going to be moles times molar mass. So 0.832 moles times 40.10 grams per mole. Using the full calculator number, my answer is 3 sig digs, 33.4 grams. Now it says, how much silicon carbide will you expect to produce? Now, what we calculated was the theoretical. What we want to calculate is the actual. So we have our formula, percent yield equals actual over theoretical times 100%. So we're wanting to find the actual. So I'm going to move theoretical to the other side. So I'm going to multiply these. And the opposite of multiplying by 100 would be to divide by 100. So to get the actual value, we are going to take percent yield. We are going to multiply by your theoretical value, and we're going to divide by 100%. So my percent yield given in the question was 96.7%. My theoretical was 33.4, and don't forget to use the full calculator number. And then we're going to divide by 100%. You'll notice that my percent signs will cancel out. So I'm going to take my answer, times it by 96.7, and then divide by 100. And in 3 sig digs, I have my answer being 32.3 grams. Again, if I was to mark this question, 1 mark for calculating moles, another mark for your moles ratio, 3rd mark is for answering the problem, getting mass, 4th mark is for formulas and substitution, 5th mark is for the answer of what is the actual value, and the last mark, the 6th mark, is for 3 sig digs, units everywhere. This question is also out of 6.